Hello everyone, here we present our paper, 3D Spatial Understanding in MLLMs, Disambiguation and Evaluation. Our motivation is to enable smooth communication between robots and human workers, especially in spaces with many objects. To do that, robots need to understand spatial language clearly and avoid ambiguity in complex environments. Existing work in visual grounding focuses on helping models locate a target object based on human instructions. Moving forward, in environments where robot assistants work alongside humans, it's important that the robot can help the human locate a specific object, especially when there are many similar ones, which we call distractors. To do this effectively, the robot's description must be precise enough to clearly distinguish the target from the distractors. For training 3D understanding, our experimental setup uses point clouds from ScanNet to represent indoor scenes, along with language annotations from Refer-It 3D. The model takes as input a 3D point cloud of an indoor scene, along with a target object that is known to the robot but unknown to the human. This target can come from any upstream task, provided as a bounding box or an object ID. The objective is for the robot to generate a sentence that clearly disambiguates the target from similar objects. It should use a precise description and refer to another anchor object to guide the human toward the correct one. Here is our pipeline. To ensure that the generated sentence exclusively describes the target, we first identify all distractors and encode the relative spatial relationships between objects. These visual inputs are then passed through a fine-tuned large language model to generate the final description. For evaluation, we first used conventional metrics such as blue and rouge. While these provide useful insights into how similar the generated sentence is to the reference, they fall short when it comes to evaluating spatial understanding. These metrics don't fully capture whether the sentence effectively disambiguates the target in a 3D scene. Here are some examples. Sentences 1 and 2 are actually correct and effectively describe the target, but they receive low scores under conventional metrics. On the other hand, sentences 4 and 5 are misleading and fail to disambiguate the target, yet they receive high scores simply because they are similar to the reference sentence. This highlights the limitation of these conventional metrics. To further verify the spatial understanding in our generated sentences, we use existing 3D visual grounding models. We train these models from scratch using the sentences generated by our LLM and compare their performance to models trained with human annotated ground truth. The idea is simple. If our generated descriptions are truly effective, then the visual grounding model should learn spatial understanding just as well as it does with human-provided sentences. During our experiments, we observed some limitations. One key challenge is viewpoint dependency. For example, descriptions like facing the window, the armchair on the left. Another limitation is handling non-rigid objects, such as humans, animals, or towels. These are challenging due to their complex shapes and the lack of large-scale training data for such categories in 3D scenes. Or action-oriented instructions, such as the chair behind the person sitting, which require the model to recognize human actions. We also observed a dataset real-world performance gap in situations involving uncommon objects, dynamic cameras, and human movement. Hello, thank you for watching. For more details, please check out our paper.